All right, let's look at the questions for checkpoint 15. So question one, we have this function in X and Y. So I've told you there are two critical points. So part A is to find them. So let's do that. So how do you find critical points? Critical points on a multivariable functions are when all of the partial derivatives are equal to zero. So step one is to find all the partial derivatives. So how many independent variables are there? There are two. So I need to find two partial derivatives. So the partial with respect to x. So let's just do term by term. So we have 6 terms. First term here, 1/2 x squared. So we can use the power rule. The derivative of x squared is going to be 2x. 2x times a half will be x. This next term is y only, so it vanishes. This next term is y only, it vanishes. This next term, negative 3xy. So what's the derivative of x? Derivative of x is 1. So all that remains here is what's multiplied by it. So that's negative 3y. X minus 3y. 9y is in y only, so that vanishes. Next term is negative 9x. That derivative is 9. So here is this derivative in, so the partial derivative of in terms of x, sorry, the partial derivative of f with respect to x is x minus 3y minus 9. So how about with respect to y? So now we'll just go through these terms again. First term vanishes because it does not have a y term. 3y cubed. So power rule, what is the derivative of y cubed? That is 3y squared. So times y, that becomes 9y squared. What's the derivative of y squared? That's 2y. 2y times 9 is 18y. The derivative of y is 1. So what's left is negative 3x. Derivative of 9y is 9. And this x term falls off because it does not have a y in it. Okay, so those are my derivatives. Just want to make sure I agree with what I did earlier. Okay, so critical points happen when these are equal to 0. So basically, I'm going to have to solve a system of equations here. So this top one, I have x minus 3y minus 9 equals 0. What I'm going to do here is I'm going to basically solve this top one equal to x. I mean, so I have two equations, two unknowns. There's a kind of a lot of ways you can go about these. Here's one thing I'm noticing that might be able to help. I'm going to take this first one and solve for x. So x equals 3y plus 9. So I'm going to use this to help me get my system of two equations, two unknowns, to only one unknown. So how is this going to help me do that? So everywhere I see an x, I'm going to replace it with 3y plus 9. So I'm going to take this. So basically, I've distilled this first equation into x equals 3y plus 9. So now I'm going to take this relationship and basically fold it into this bottom relationship. So that becomes 9y squared plus 18y minus 3. I'm not going to put x. I'm going to put, in place of x, 3y plus 9 plus 9 equals 0. Okay, so what happens here? 9y squared plus 18y minus, and I'll distribute 9y minus 27 plus 9 equals 0. Thank you, Zoom. All right, 9y squared, collect like terms, plus 9y minus 18 equals 0. Everything is divisible by 9. So I through by 9 and I get y squared plus y minus 2 equals 0. That factors into what? I believe that factors into y minus 1. Y plus 2 equals 0. So I get two values of y. So y equals -2 and +1. Okay, so what are the x values that go along with those? So when y equals -2, I get that x equals, I can use this top value here, or this top equation here. If I plug in -2 for y, I get -6 plus 9, that's 3. Okay. So basically one of my points is going to be 3, -2, and then I'll leave a blank because I'm going to plug in that and get z. Because I want to get ordered triples. So y equals, was it 1? So that gives me that x equals, when I plug in 1 here, I get 3 times 1 plus 9, and that's 12. So 12, 1, and then, so what's my z value going to be? All right, so let's plug in and figure out what these are. So when I plug in 3, so I get 1/2 times 9, 9 halves. So 9 halves plus 3 times -8. Plus 9 times 4. Minus 3 times -2. Plus 18. Plus 9 times y minus 18. Cool. Minus 27. All right, so 24 plus 36. That's 12 minus 27. Minus 15. So I believe all told that's minus 10.5. Minus 10.5. And then what about when I plug in 12 and 1? So 1/2 times 12 squared, that'll be 72. Plus 3 plus 9 minus 3 times 12 times 1. So that's minus 36. Plus 9 times 12, that's plus 108. Wait, no. Plus 9 times 1 is 9. Minus 9 times 12 is 108. 72, 75, 84. Minus 36 is 48. 57 minus 108. Negative 51. All right, so I'm not as confident about the z values as I am about the x and y values. Okay, so, but I am almost certain about the x and y values, which are of far more importance for what we're going to do next. So now we're going to classify those critical values. So how do we classify those values? So for part B, we classify these values through the second derivatives or second partial derivatives. So now I need all like the second order partials. So now I need this. So what is this partial? So that comes from taking the first partial with respect to x and taking that partial with respect to x again. So the only x term in there is x. So if I take that derivative with respect to x, I get 1. All right, now I take the other unmixed partial. What is that derivative with respect to y? That should be 18y plus 18. 18y plus 18. And now we do the mixed partials. What is fxy? That should be -3. And what is fyx? That should be -3 as well. And I'm not sure if the videos pointed this out, but the situations are extremely rare when these are different. So I'm pretty sure that in any of the functions we're going to look at, those mixed partials, the order should be irrelevant. Shouldn't not matter what order you take the derivatives in. All right, so now how do we classify? So we find this value D, and the way we find this value D is like this. It's from fxx, fyy, make sure I get this thing totally right. Okay, minus fxy squared, because it really does not matter what the order is. So let's just do this point by point. And really it matters, and you take these for whatever the values are. So let's handle it first for the point, 3, -2. So fxx, that was a constant. So fxx is 1. What was fyy? Fyy is the only one that's going to change from point to point. So what was fyy? That is going to be 18 times -2, so -36 plus 18, -18, minus fxy squared, so minus 9. So that is equal to -27. So it doesn't really matter what that number is. What really matters is its sign. So it's negative. So what does it mean when it's negative? That means it is a saddle point. So we have a saddle point at that top point. Now, what do we have at our other point? So at 12,1, we have what? So we're going to do the D test again. So fxx for this case is always 1. fyy is the only one that changes. So 18 times y. So that's 18 times 1 plus 18, 36, minus fxy, so minus 9, because fxy was a constant -3. So we get what? We get 27. So that's a positive number. This is the case where you have to look a little deeper. So when D is 0, then you have to look at fxx. So when D is 0 and when D is positive and fxx is positive, that means you have a local minimum. So D is 0 and fxx is 0. So this one right here is a saddle. This one right here is a local minimum. All right, moving on to question 2. All right, so a manufacturer wants to make a rectangular box. So we have an optimization question. The boxes have to enclose 20 cubic feet of space. So I'm going to draw myself a small picture just to kind of organize what's happening here. So a rectangular box. So X, Y, Z dimensions. All right. To be durable enough to ensure the safety of the product, material for the sides of the boxes will cost 10 cents per square foot, while the material for the top and bottom will cost 25 cents per square foot. So A, write a function for the cost of the box in terms of 3 dimensions. All right, so I'm going to write a equation for the cost of the box. So this is going to be so the cost in terms of, I called them X, Y, and Z. You could have called them something different. So the sides of the most expensive are the top and bottom. So for me, X, Y are the really expensive sides, right? Because X, Y are the top and the bottom. So those are going to be, so basically X and Y, those are going to cost 25 cents to make an XY side, right? And there's going to be 2 of those. So what are the cheap sides going to be? Well, the cheap sides are going to be 10 cents, and I'm going to make those are going to be the side walls. So those are going to be XZs. There's going to be 2 XZs, and those are also going to be XYs. No, not XYs, YZs. All right, can I consolidate some things here? So 50XY plus 20XZ plus 20YZ. All right, so here's my cost function in terms of all 3 dimensions of the box. All right, so that was part A. So for part B, I want to write an equation for the constraint. So what's the constraint? The constraint is that basically I need to hold exactly 20 cubic feet of space here. So how do I find the volume of a box? By just multiplying all 3 dimensions together. So the constraint is going to be what? X times Y times Z equals 20. So there's my constraint. So part C now is to combine those 2 things, and that should help me get my answer from A to get my cost function down to only 2 variables. So for B, I'm going to solve for one of the variables. I don't really care which one. I'm going to go ahead and do Z. I'm going to say that Z is equal to 20 over XY. And that is going to allow me to do this. That's going to allow me to write C as a function of X and Y only. So C as a function of X and Y will be this: 50XY plus 20 times X times 20 over XY plus 20 times Y times 20 over XY. And we can clean some things up. 50XY, X cancels X, plus 400 over Y plus 400 over X. All right, so this is a good simplified objective equation. Would rather deal with 2 independent variables than 3. All right, so we're good with C. So now we're going to use partial derivatives to optimize. So basically, we're going to do the same kind of technique that we did with 1 to find the optimum here. So I want to find critical points. So how do I find critical points? I'm going to use partial derivatives to do that. So partial derivative with respect to X, term by term, this will be 50X. The second term has no X in it. So 50X plus, I'm going to rewrite both of these things, to kind of make derivatives easier to think, maybe easier to think about, at least easier to think about in terms of power rule. 400 times X to the negative 1. So 50X minus 400 X to the negative 2. And C sub Y equals, I think I did something wrong here. This derivative 50X of 50XY with respect to X should be 50Y. And this one should be 50x minus 400 y to the negative 2. And that term vanishes. And then I set both these to 0. What do I get? $50y equals 400 over x squared. And 50x equals 400 over y squared. Okay, so before I go too much further, I'm going to divide both of these by 50. So that gives me y equals 8 over x squared, and x equals 8 over y squared. All right, so where should I go from here? So I have two equations, two unknowns. So I think I'm going to do something like what I did before. I'm going to take one of these expressions and basically plug it into the other. I have that x equals 8 over y squared, so I'm going to do something like this. Y equals 8 over 8 over y squared squared. So y equals 8 over 64 over y to the 4th. So it's kind of getting weird looking. How can I keep going with this? I don't like fractions within fractions. How can I deal with this? Well, I can multiply both top and bottom by this reciprocal. So that'll cancel that. So then I get y equals 8y to the 4th over 64. Now I don't have fraction within a fraction anymore. I can multiply both sides by 64 and I get 64y equals 8y to the 4th. There's no chance that y could equal 0, so I can divide both sides by y. I can divide both sides by 8y. If I do that, I get that let's do one piece at a time. (64) equals 8y cubed. Y cubed equals 8. Y cubed equals, nope, I already did that. So I think I found a good value for y. I think that y equals 2. So if y equals 2, then what does that mean about x? If y equals 2, that means that x equals 8 over 2 squared, which is 2. So y equals 2, x equals 2. And what does that mean about z? Z equals 20 over xy. So z equals 20 over 2 times 2. So z equals 5. So basically, final answer, xyz equals 2, 2, 5. This is the cheapest thing I can make, 2, 2, 5. So part E, I've run totally out of room, so I will leave that to you. You can basically use a D test to make sure that your X, Y, and Z conditions, or just X, Y conditions, actually do give you a local minimum and not something like a saddle point or a local maximum. All right, moving on to question 3. All right, so this Cobb-Douglas production function is used in business and economics to model productivity based on labor and equipment costs. So suppose we have a specific one. of this form where X is the dollar amount spent on labor and Y is the dollar amount spent on equipment. So we can use Lagrange multipliers. So that implies to me that we have a constrained optimization situation here. So we're trying to maximize productivity, given that we have a total amount of money we can spend. So this right here is the constraint. This is how much money we can spend. So we want to optimize productivity. We want to optimize F. So we want to optimize F constrained by what? We'll call it G, but what is G? G is going to be this $1.5 million. So $1.5 million is what? So that's going to be the total spent on labor and equipment. Well, that's going to be X plus Y, right? X is the dollar amount spent on labor. Y is the dollar amount spent on equipment. So our constraint equation is going to be this: G of X and Y is equal to X plus Y equal to 1,500,000. So basically, these are the two equations that are going to govern the situation. F is the thing we're trying to make the most of. G is the thing that's going to make it hard to do that. Basically, G is a requirement we have to hold to. So we need all these partial derivatives. So the partial derivative of F with respect to X is 50 times, got to use the power rule on X to the 0.4. So that'll be 50 times 0.4 times X to the negative 0.6, because that's 0.4 minus 1 times Y to the 0.6. What does that come out to be? That comes out to be 20 Y to the 0.6 over X to the 0.6. With respect to Y, that comes out to be 50 times 0.6 times X to the 0.4 times Y to the negative 0.4. So what is 50 times 0.6? That's 30. So 30 times X to the 0.4 over, stop connecting. All right, so here are my two partials of F, but now I'm going to do something similar with G, and those are going to be much simpler. Those are going to both simply be 1. So then how do I continue this? Basically, the way Lagrange multipliers work is I want, in both the X and Y directions, I need these to be true. I need this partial to be some multiple of the partial derivative of the constraint, and I need the partial of the objective function to be the same, like basically the same multiple of the partial of the partial in the Y direction of the constraint. So I don't care what that multiple is, but it has to be identical across both directions. So this is kind of our approach here. So let's start filling in those details. So from there, I have this 20 Y to the 0.6 over X to the 0.6 equals lambda times 1, so lambda. 30 times X to the 0.4 over Y to the 0.4 equals lambda times 1, so lambda. But we're missing something, because how many unknowns do we have here? We have X, we have Y, we have lambda. That's 3 unknowns, but we have 2 equations. So we need a third equation. So the third equation I'm going to use, the only equation I have left for me is x plus y equals 1.5 million. I want to point out that we can't use the thing we're trying to optimize because that's not an equation. It's a function, but it's not set equal to anything. Whereas the constraint equation, x plus y is equal to 1.5 million. Those are two expressions equal to each other. So that'll be my third equation. So here is my system of three equations, three unknowns. And I pointed this out in the discussion question video if you watched that previously. But I don't really care what the value of lambda is. It's a means to an end. It kind of helps me solve the system, but all I really care about is what x and y are. So I say that to kind of introduce this. I have these two expressions here that are equal to lambda. So basically, I'm going to use that to set them equal to each other. So 20y to the 0.6 over x to the 0.6 equals 30x to the 0.4 over y to the 0.4. Something really convenient that happens with these, what are the two names? Cobb-Douglas equations, is that when you cross multiply, the fact that these exponents add up to 1, when you cross multiply these partial derivatives like this, these exponents always stack back up to 1. So now when I cross multiply these, what is 30x to the 0.4 times x to the 0.6? That comes out to be 30x equals 20y. That came out very nice. So now my system of three equations that didn't look very friendly, that had a bunch of decimal exponents. So I got 30x equals 20y. That's one equation. And x plus y equals 1,500,000. So from there, let's do this. Let's divide this first equation. Let's divide through by 20. If I do that, I get y equals 3 over 2x. Now from this, I think I can take this thing here. So I whittled 3 equations down to 2. Now I'm going to whittle that down to 1. So x plus 3 halves x equals 1,500,000. So that becomes 5 halves x equals 1,500,000. So what does that tell me about x? Let's find out. So x is equal to 600,000. Which means in turn that y is equal to 900,000. So what did we just find out? That if we want to maximize productivity, we need to spend $600,000 on labor and $900,000 on equipment. So using Lagrange multipliers, that's how under these constraints, we optimize productivity by spending, basically by dividing up our total amount of resources on those two categories. And that's all for checkpoint 15.